Hi. Okay, we're just finishing up the lesson on the vector equation of a line. Just reminding you that the vector equation of a line is r equals a known point on the line, so I'll just make one up. So it could be like 5, -2 plus t times our direction vector, which I can say would be, well, let's do 4, -1. For a direction vector. So that's the vector equation. Then the parametric equations. So this is vector, parametric are going to be x equals 5 plus 4t and y equals -2, t times -1 is -t. And then the symmetric equation is going to be x minus 5, so we're pretending to get t by itself here, so we'd subtract 5 and divide by 4 equals y. If we were getting t by itself here, we'd add 2 and divide by -1, the coefficient of t, so that would be our symmetric equation. And then just noticing where we see the point. So in the vector equation, this is the known point on the line. In the parametric equation, this is the known point on the line, 5, -2. And in the symmetric equation, we get the known point on the line by taking the opposite signs and making the point 5, -2. Similarly, we can see the direction vector in each equation. So here's our direction vector, 4, -1. Here we take it from the coefficients of t, 4 and -1. And in the symmetric equation, so in the parametrics, they're the coefficients of t make the direction vector. And in the symmetric equation, the denominators make the direction vector. So a little recap of the three kind of vector forms of the equation of a line. We have a vector equation of the line, parametric equations of the line, and the symmetric equation of the line. Okay, so we're just going to finish up those last two questions. So the equation of a line, so this is given in standard form, is 2x minus 3y plus 12 equals 0. Write the equation in vector form, parametric form, and symmetric form. So, in order to get the equation from standard form into vector form, we need 2 points because we need a direction. And often the easiest 2 points to get from standard form are the x and y intercept. If they're right on corners and we don't have to involve fractions, all the better. So in this case, if I was finding the x-intercept of this line, we know we set y equal to 0 and solve for x. So that would be 2x plus 12 equals 0. Subtract 12 on both sides. And we get x is -6, which means that -6, 0 is a point on the line. Let's call it point x. So I'm going to come back up here. We know we have point x being -6, 0. I'm using a capital X because it's a point. And then our y-intercept we know we can find by setting x equal to 0 in the equation. And we would get -3y plus 12 equals 0. Subtract 12 on both sides. Divide both sides by -3. And we get y is 4. So capital point capital Y we could think of as 0, 4, the y-intercept. So using the x and y intercept, we now have 2 points on the line, and we can find the vector from point x to point y. So 0 minus -6 is +6, 4 minus 0 is 4. And from that we can make a direction vector. See if there's a smaller scalar multiple, we can divide each term by 2. And so our vector equation, we can choose either point x or point y. I'll just choose point x because it comes first. plus t, our parameter, times our direction vector. So based on this being our vector equation, it's easy to get our parametric equations. So they're going to be x equals -6 plus 3t, and y equals 0, which I don't need to write, plus 2t. 0 plus 2t. So that's our parametric form. And in symmetric form, so I want to get t by itself in this equation, so I would do x plus 6, add 6 to both sides and divide by 3, equals y. Now I don't have to add or subtract, I just need to divide by 2 to get t by itself, so equals y over 2. So there's our symmetric form. Okay, and our last question, classify these two lines as either coincident, so this means they're actually the same line. So they coincide with each other, just written in different ways. Remember, there's an infinite number of vector equations of a line. So they could be the same line, just not look like it, or we have to do some investigating to see if they are in fact the same line. Parallel and distinct, so that would mean we'd have lines that were, actually I'll just use a piece of paper. So if we have an XY axis, parallel, so exactly the same direction, but two separate distinct lines. Okay, so that's parallel and distinct. Perpendicular, so meeting at right angles, or none of the above. So in order to figure out this, we're going to start off by figuring out the direction vector of each line. So let's call this one's called line 1, so R1, and this is line 2, R2. And looking at the direction vector here, we can see that M1 is -6, 3, the direction vector of line 1, and M2 is 2, -1. So the first thing we want to do once we get our directions is to see if they're parallel or not. In other words, are they scalar multiples of each other? So in this case, if I multiply 2 by -3, I get -6. If I multiply -1 by -3, I also get +3. So that tells me that M1 is actually -3 times M2. Okay? Which means that, so since the directions are scalar multiples of each other, we either have the same line, so we either have coincident lines, or we have parallel and distinct lines. So now that we know that these two lines are parallel, we want to know, are they in fact the same line, just with a different point here that happens to be along the same line, or do we have two different lines that happen to be parallel? Okay, and the test for that is going to be, is a point we know on line 1 also on line 2? Because we have two lines that share a point and the same direction, that means they would be the same line. So we can do that test here. So our test is going to be, so we're testing to see if they're coincident lines. So is the point -9, 10, which we know is on line 1, also on R2? So is this point that we know is on line 1 also on this line? If it is, then they're coincident lines. They're exactly the same line. If not, they're parallel and distinct. Okay? So, how do we test that? I would say parametric equations. So let's get the parametric equations of this line. So I know that to get an x, it would be 3 plus 2t. And to get a y, it would be 4 minus t. Now we're testing to see if the point x being -9 and y being 10 is on this second line. And then if it is, we'd have to get the same t in both cases. So I would subtract 3 on both sides, divide both sides by t, and I would get t is -6 when x is -9. And similarly over here, if I get t by itself, I again get t is -6 when the corresponding y value is 10. So since the t values both turn out to be exactly the same, so therefore R1 equals R2, meaning the lines are coincident. If these t-values had not been the same, we would have had two lines that were parallel and distinct. Okay? Now, say that these direction vectors had not been scalar multiples of each other, so the lines weren't parallel, then we could immediately cross off coincident and parallel and distinct as possibilities, and we're left with either perpendicular or none of the above as our two possibilities. Perpendicular, the dot product of the directions would have to be 0 for the lines to be perpendicular, so remember that. Perpendicular means the dot product of the direction vectors is 0. That's how you'd have your two lines being perpendicular. And then if none of those three things were true, then you would select none of the above. Okay, so that is the end of our introduction to the vector equation of a line.